So today we're going to continue our discussion into volume of solids by rotating a region around some curve. In this case, we're going to go about a y equals curve. We're going to sketch the region, talk about the solid, talk about whether it's a disk or a washer. And today's problem is this. Given the curves y equals x to the fourth and y equals 1, and they're going to rotate it about the line y equals 2. So if I graph these just quickly, x to the fourth, hopefully we all recognize as that curve on the y and x axis with an intercept of 0, 0. Y equals 1 is going to be this line, and y equals 2, whoops, is going to be another horizontal line. This is our rotation axis. So we're going to rotate that region around the axis here. And hopefully you can see that there's going to be a hole, all right? And we're going to do that part. So since y equals 2 is parallel to the x-axis, this is going to be an integral with respect to dx. Because our cross-sectional area we're going to take, when we cut this, we are going to get a washer. So we're going to clean this up a little bit on a new sheet and start writing this out. So I have the graph of the function here, and then there's the region we discussed, and we know that the volume is going to be from A to B of the cross-sectional area dx with respect to dx. Razor thin sections, washers around. And when I draw the washer, it's going to look like this. And you're going to have some RO and some RI. And I can see the area of this donut or this washer is simply pi RO squared for the outside minus pi RI squared for the inside, dx. And I'm going to get RO and RI in terms of x so I can make the integration. I also can see that the limits of integration here are negative 1 to 1. So if I pull all this out, I can factor pi, which I usually do. I go negative 1 to 1. And I'm going to have to figure RO squared minus RI squared dx. I have to calculate those. So I'm going to jump to another page here for a second and kind of blow up that region here. Alright, I see y equals 2 when we're rotating this region, R, about it. And again, I've marked RI and RO as we rotate it around this way. Hopefully you can see then that this line is y equals 1, the bottom line is y equals x to the fourth. If I start with RI over here on the left, you can see that RI and this height here, which I will call y, but y is equal to 1. So again, I see RI plus y has to be 2 when I sum those two distances, and they're both positive. So, but y is equal to 1, so I can go RI equals 1, or y equals 1, and then I move it over, I get RI is 1. And you can see that RI is 1. It stays the same the whole way here. Awesome. Likewise, I can do the same over here, but this time the y is equal to RO plus y is going to be 2, but this time y is x to the fourth. So RO is 2 minus x to the fourth. So RI is 1 and RO is 2 minus x to the fourth. So I can plug those in to my function. So I get pi negative 1 to 1 RO 2 minus x to the fourth quantity squared minus, and I'll write it out as 1 squared so we see that. And that's my integral. And if this was the calculator section of the AP test, we would simply plug this in and get a value. Now if we do that, I did it by hand now, I haven't checked this, but I get this for the volume. I did do the integral by hand, I'll put that up. And again, if it's good practice you want to pause it, but that's where the value came from. And again, the big mistakes I see all the time, we forget to subtract, I almost did that. And we forget that a binomial squared becomes a trinomial. And when we combine the like terms, alright, we can get to an integral of x to the 8th minus 4x to the 4th plus 3. And you notice this is an even function, which means it's symmetrical about the y-axis. So instead of doing the limit from negative 1 to 1, I know that this curve, that when I rotate this section around that axis, I can just do half of it and change the limit of integration here from 0 to 1 and just multiply the result by 2. And when I do that, it makes the integration here much more easy or less difficult. So again, an example of finding the volume of a region rotated about an axis. Keep practicing.